So we'll begin. Whoever is there, there. Whoever is not there, not there. So we were discussing about Fourier Z transforms, signals and systems and their behavior, poles and zeros, all kinds of things relating to signal processing. So I will not start speech processing today. Uh, Today was initially, as you know, designated as a holiday, but it has moved to tomorrow. So I will just revise all those things and add a few more other and discuss a few more other important things along the way. So we discussed about Z transform. If you have a LTI system, then it is related by convolution in the time domain, and the same thing using Z transform properties we can uh, uh, express as multiplication, simple multiplication of some polynomials of Z. It will be some polynomials of Z. So your system transfer function, as you can see, it is a relation between your output and input, and that gives the behavior of the system. So we were discussing about various roles of poles and zeros. So let me recapitulate some of them once again. Where was it? So this is your Z plane, and let's say your we can express, let's say, h of Z, the system transfer function, as some uh, in some factors of Z. So Z minus, let's say, Z naught, Z minus Z1, something like that, and Z minus Z2, Z minus Z3. Obviously, what you are seeing here is in this, when Z equal to Z0 or Z1, the transfer function will become 0. So hence, these positions, these values are called the zeros. And in the pole zero plot, you will find some Z0, Z1, let's say, Z0, Z1, something like that. They represent as zeros. Now, in the same way, if Z equal to Z2 and Z3, however, HZ does not exist. It cannot be defined, or we say it is infinity. So, so more correct way to say is that we cannot find the convergent value of HZ, convergent solution. So those places, those positions, those values where HZ is not defined, HZ is goes to infinity. Those are called the poles. The location of poles and zeros gives a lot of information and helps us analyze the system in a very simple manner. Unlike a difference equation in a time domain equation, which is very complex to analyze and find some output and relate the output and input of, if it is a very large equation, which happens in our normal applications. So let's we were analyzing what happens when we have real poles and complex conjugate pools, and why do we even and what is a resonator? Why do we even need them? What is the uh, purpose of all designing systems with resonators and so on? So let's take some pole here. It's a real pole. So let's assume z is some a. So z minus a. And obviously we need to provide an ROC with it. Okay. So we assume a is less than 1, some 0.5 or something. Let's say. What is the advantage of that? If a is less than 1 and if the impulse, you should remember that impulse response in the time domain and in the z domain or z transform domain, we have the transfer function. So if it is a right-sided or causal, it is also called causal. Right-sided means also causal. Then it will result in a stable, it will result in a stable system because it also includes the unit circle. If it includes the unit circle, you are guaranteed that it will result in a stable system. Even if it is does not include the unit circle, it is possible that system might be stable, but this is a guarantee that if you have uh, if the unit circle is included in your ROC, then it is a stable system. So let's assume it's a stable system, right-handed system, causal system. So and your it is a real pole within the unit circle. So as we said, it will be outwards of the if it is a right-handed signal, it will be outwards. The ROC will be outwards. That's how we have. Let's say we are designing it like this. So we get a right-handed causal signal, and we'll deliberately put the value of a as less than 1. So unit circle is included, and we get a stable system where Fourier transform is guaranteed to exist. So if we have this, so hz, we can write it as z by z minus a into z inverse. So let's go back and what do we have in the ROC? So if you check the basic Z transform properties and standard solutions of some of the Z transforms, you will see, for example, here what it is. You have Z by Z minus A, Z greater than modulus of A to the power n un. So what we will get for this part, sorry, for this part, it's A to the power n un, which is a right-sided signal, causal signal. But we have also this part. So you can say that you will find that there is a property of Z transform. What that property says? What that property says is this one. This is a very important property. I told you last time. Z to the power minus, if you shift in the time domain, as Z to the power polynomial gets multiplied in the Z transform domain. So what it is happening here is it means that if this is so what will happen here is, just a minute, e to the power n minus 1 un minus 1 will be the resulting impulse response. This is the impulse response. And where A is less than 1, so that it is a decaying response, so it is a stable system. So this is a simple example. So what will happen in this case? It is a from n equal to 1, 2, and to infinity. It is a since A is less than 1, if 1 is this, let's say something value, and it will keep decaying. It's a stable system. So real poles, if you have real poles in the tensor function, this is its basic role. It either says that the system, if A is less than 1, the system tensor function is decaying with time, exponentially decaying with time, or it is uh, increasing with time if A is greater than 1, which is unstable. So that's his basic role. Now let's come to uh, resonators. So this is our unit circle, z equal to 1. So you can only have, if you have a complex pole or 0, if you have, then it will always be in pairs. It will have also a complex conjugate. It is mandatory. Why? Because you see some hz equal to yz by xz equal to, let's say, we wrote in terms of factors. But those factors, if you expand it, it is uh, z to the power something, z to the power uh, some n, let's say z square or something, z square minus z 1 minus 5. Let's say some polynomial it will come. Similarly, z to the power 5 minus z4 plus z cube, something, some value will be there. Of course, there will be some a2, a1, something. Some values will be there, but it will come out to be a polynomial. Now, if you go and multiply, cross multiply this, what will happen is, let's say a2 z square minus a1 z1 plus, let's say, a naught into xz. That will become, let's say, some a4 z4 minus a3 z3. Let's say yz. Now, if you take the inverse z transform of all this, what will happen is you will get see a2 x n plus 2. If you go through the z transform properties, minus a on a, these are simple properties, a of x n plus 1 plus a naught xn equal to uh, a4 yn plus 4 minus a3 yn plus 3, like this. So now these coefficients, they are all real coefficients. They have to be real. These are our real numbers. These are all real numbers, and we'll multiply them, and the equation comes in real form. These are our outputs and inputs. They are related, and we multiply in the time domain by some real values, some amplitude. That's how we do it. So if these things have to be real, then you have to have complex conjugate. If you do not have complex conjugate, if z minus z1, z minus z1 star is not there, these coefficients will be uh, imaginary or complex, and then our analysis, our system will break down. Complex numbers has its purpose, but obviously the time domain, why will we uh, multiply with a complex number? We will not achieve anything by that. So uh, that's why, because our coefficients in the time domain difference equation has real coefficients. So in the Z transform, if we have a complex pole, it should also have a complex conjugate pole. Similarly, a complex zero, a complex conjugate zero. They come in pairs. So now let's take this. I was talking about resonator. Let's take this. Let's imagine that this, we call it some R naught. Uh, both are R naught because uh, let's imagine like this, something hz equal to 1 by z minus z1, z minus z2. Let's imagine there are no poles, just sorry, z1 star, and z1 is some uh, r naught e to the power j omega naught. I hope you know how to write in polar form. So this is what it is. So let me go back once. All of you are hearing, I think there is no issue with internet. Like last time, yeah, there is no issue with your internet. Yeah, okay, all of you are hearing, okay. I just wanted to check. Last time there was a problem anyhow, so I'll go back. So in polar form we will write like this. So in these two places your hz does not exist, or it goes to infinity, however you put it. So so then z1 star will be what? R naught e to the power minus j omega naught. You should know Euler's formula. Guess you know what is Euler's theorem or Euler's formula. E to the power j theta equal to cos theta plus j sin theta. So from that, using that, you can represent any complex number in this form. So that's all. So if you have this, now look at what it is. Now let's try from the Z transform. We have we know that how can you get h e to the power j omega? By putting z equal to where in the unit circle the Z transform becomes the Fourier transform. When z equal to 1, since z equal to r e to the power j omega, we'll get the Fourier transform of the signal, or in case here the system of the system impulse function. Okay, so we'll put z equal to e to the power j omega, and then what happens? So it will be e to the power j omega minus r naught e to the power j omega naught, and e to the power j omega minus r naught e to the power minus j omega naught. Now you can do this algebraically also. So then you can plot omega, and then just plot the magnitude, just simply magnitude of this magnitude spectrum. You can plot both magnitude and phase, but just plot the magnitude spectrum. what you will find that there will be two peaks at omega naught and minus omega naught. Now let us see how to visually represent or analyze why there are two peaks. So I will create another. Right. So we had these two. We can represent these two as Z1, Z1 star. What do I have? Z minus Z1, Z minus Z1 star. And what is Z? Any arbitrary Z. When Z equal to e to the power j omega, this is what it is. Any arbitrary point where this is omega. R equal to 1. So this is nothing but a distance between the vectors. Let's call it d1. Again, d1 star. Now when omega equal to omega naught, this distance will become very, very small. This d1 become very, very small. And as z1 less than 1, but it approaches 1, it approaches the unit circle, this distance is greater than 0 but nearly equal to 0. So then what happens is nearly equal to 0, this distance becomes nearly equal to 0. So this hz where z equal to e to the power j omega, that means our Fourier transform we are trying to find, it becomes what? If you take the magnitude, it becomes very, very high. And when you put Z1, let's say Z1, you put somewhere on the unit circle, if you put the poles in the unit circle itself, then obviously it goes to infinity, and you know ROC cannot include, should not include the poles. That means the Fourier transform does not exist. It's it was j omega goes to infinity, means Fourier transform does not exist. ROC does not include the unit circle, so obviously Fourier transform does not exist. So this is what it means. But when Z1 is very close to the unit circle, we can design a system which we call, or we see many natural systems we will find in our speech processing course, how we model the source product, the voice production or speech production system from the larynx or the voice box to our lips. We'll find that there are resonators, and this phenomenon occurs in nature in many forms. So now just look at this equation: z minus z1, z minus z1 star. So it will, sorry, it will be a 2-degree polynomial, some a2 z1 plus a1 z1 plus a naught, something if you break it down. Correct? So now let's go back to your classic look here. Look at your sine and cos functions. What are their z transforms? See, there is a 2-degree polynomial. in the denominator. Of course, there is something on the numerator also, but we can take care of that. We can say they are delayed versions of, z square means multiplying by z square means delaying the signal by two indexes. Same thing. Cos omega naught can be considered as a constant and so on. So you see, so these are sinusoidal signals. So what is a resonator? So what a resonator is giving is, um, where is it? Oh, sorry. So what the resonators are giving are, I will again add another page. I think it will be good for it. What the resonators are giving are in time domain, where n is your index, discrete time domain, some form of sinusoids, some sinusoidal waveform. And you must have heard in your physics, basic physics courses, what is resonance means. It's something, you have a quartz crystal or something, it has a particular resonant frequency. Uh, if you are putting a frequency, giving a signal of same frequency as its characteristic resonant frequency, it will blast and produce a huge output. So it's the same kind of concept here. See, a sinusoid never dies down. It's infinite. So along with resonant, uh, resonator, this we got no z minus z1, z minus z1 star. We'll also have some real, real poles. Now, what is the use of real poles? Real poles, it will die down. We saw just previously we discussed. And then this resonator is there. So it becomes a dying or a decaying sinusoid kind of thing. So this is how we'll again discuss this during our speech processing. Uh, uh, we'll discuss in brief during our speech processing how we model the vocal tract system and what happens. So, but this is where these poles and zeros analysis comes into the picture, particularly in our speech processing uh, domain. So let's see what we have next. So we discussed about all these things. Causality. What is a causal signal? Causal signal is where is it? Yeah. So n less than zero causal system here it is saying. So it's again system and signals are interchangeable things. We define a system in terms of its impulse function, which is a signal. So that's why I say signals and systems or vice versa are interchangeable. So anyhow, it's a mathematical formulation. So n less than zero, there is nothing. Only from n equal to n greater than zero, there are some values. Rest are all zeros. So this is what is called right-handed or right-sided signals. And what will we have? Whatever is your largest pole, whatever is your largest pole, the ROC will be outside of that largest pole. So on the other hand, if it is an anti-causal or a left-handed signal, then ROC will be inwards of the whatever pole it is. So ROC will be inside that. Excepting, I told you, Z equal to 0, Z equal to infinity, you have to check those two cases. But otherwise, that is how it is in the general sense. Yeah, again, stability. So ROC, the signal is stable or the system is stable if This is your definition of stability. Fourier transform exists, guaranteed to exist, guarantee or sufficient condition, not necessary. Even if it is not followed, Fourier transform can exist. For example, sine, cosine, even those. But uh, the sufficient, it's a sufficient condition, and Fourier transform will exist. And what does that mean? That the ROC will contain the unit circle. So causal and stable system, this is what we want. We want the ROC, the poles should be inside the unit circle, and it should include the ROC. This is causal or right-sided, and because it includes the ROC, it is stable. Now, what does this? What is the benefit of causal? I have been saying causal or right-sided. So this definition of Hn equal to 0 for n less than 0, and it has some values for n greater than equal to 0, not equal to 0. Some values, it might be 0 in between, but when in this case, what happens is, if you will do simple convolution, you will try to find out yn into xn into hn. You will find that your output is always dependent on your uh, current to your current input on all your previous inputs. For example, if you want to find your output at an index n, so it will be from some n equal to n minus 5, let's say, to n. Or it could be, it may not even include your current vision, but it will never depend on future values. So that is important, because in real time, uh, when we are getting a signal in real time, you don't know its future values. So a causal system means it dependent on the past only. It has no dependency on the future. It is dependent on current values or the past and the past, but it is not dependent on future. That's why we want the system to be causal. That's the definition of causality. And when you work through the mathematics, you will find that in order for that to happen, this is the equation that is needed. Hn equal to 0 for n less than 0. This is the standard definition of causality. The output should only depend on present and slash or past values of input. And when you do your mathematics, just simply revisit, just simple mathematics. If you do, you'll find that this is the definition that comes out. So this is what I wanted to discuss, just revisiting your last class mainly. So these are the things I have talked about already, how in polynomial form we get our this is your linear difference equation, and then you get in terms of polynomial. One important thing to note that what is recursive or IIR, infinite impulse response system, and what is non-recursive or FIR, finite impulse response system. So what happens is, if you're in this equation, if there is only yn, all this there is output has no other dependency on previous outputs, then this becomes a FIR system. Finally, if you find out the impulse response Hn, you will find that it will have a finite number of indices where it will have some values, rest will be zeros. Only a finite duration it will last. That is called finite impulse response. But if your yn, this equation has yn minus some a2 yn minus 1, it's indirectly it depends output at a particular point also depends on outputs of previous times, then you generally get what an IIR system, infinite impulse response. That means the impulse response does not end, it goes on. So please keep that in mind. Just check out once, brush up. It's a very easy thing concept to get to hold of. So then filtering is uh, as I told in the first two classes, there is a one of the basic uses of signal processing is in, let's say, enhancement or denoising of signal. So there is a signal. There is let me put it. There is a signal, but it is corrupted by noise. So if you plot its Fourier transform, you find this is there, but some place there's a huge amount of noise. So there are many ways to remove it. If, for example, your signal is completely concentrated here, then you can use something called as a low pass filter. Well, up to a certain, from 0 to a certain cutoff frequency, you will design a system, you will pass it through a system, h omega or h of e to the power j omega, continuous discrete time, whatever, does not matter. So it's the same concept. You pass it through a LPF, low pass filter, and so in the resultant, whatever you get, the output, this will not be there. Now there could be other cases where you want there is important information only in a particular range of the frequency spectrum. In that case, you might want to filter some the signal in a particular range. This is called a band pass filter. Again, in the same way, you could have just like low pass filter. If there is for some reason some information in high frequency, in the low frequency, you don't want that information, whatever be the reason. So 0 to omega c will have nothing. In the output, you will have only high frequency. Again, there is another one which is called band stop. So, for example, here you could have used band stop. So I have a signal which exists for all frequency, but in this small narrow window, there is a lot of noise is there. So we'll get rid of that by using a band stop filter. So these are the concepts you should go through, just revise. Try and this is a very simple example, RC. These are all ideal filters, as I said. Obviously, you cannot design filters so smooth and perfect. What you will get is generally filters like this. You want to design a low pass filter, it will come like this. Instead of having like this, you'll always design it like this. It's impossible almost to have a perfect ideal filter. There are lots of disadvantages of having ideal filters which you cannot implement in real life. These ideal filters will be of infinite duration, infinite impulse response. So what does infinite impulse response means? This is non-causal. That means the output also depends on future values of your input. So we cannot have all that. So we have to uh, come to some realistic trade-offs where you can low pass filter and still have a causal system. So this is where digital signal processing, I don't know whether you went through that filters, Butterworth filters, Chebyshev filters, all those. But forget about it. It's not required for this course, but it's good to have at least a idea of what those things are. So bandwidths again. Uh, Bandwidths are if you have h e to the power j omega or h of omega, whatever you take, you plot the magnitude. Magnitude square is given by power, is called generally power or power spectrum. If this is called magnitude spectrum, h of j, this one, this is called power spectrum. And what happens is when your maximum power, P max, becomes half, so this width, you call it 3 dB uh, bandwidth. Alternatively, it becomes 1 by root 2 in the amplitude or magnitude spectrum. We call it the same thing. Whether you, it's a square, so you understand what I'm trying to say. So I think you know this. You have gone through so many courses. You know how to calculate 3 dB bandwidth. So that's all. This is the same concept for signals. Yes. What is a band limited signal? A band limited signal is simply a signal where there is a maximum frequency above which no all frequency values are all zero, magnitude or zero. So it has no frequency above that, frequency components above that point. So these kind of signals we use generally, uh, we use your Nyquist theorem to sample at a particular rate. What is the rate? Greater than or equal to the maximum frequency of the signal, and then we convert it into a digital signal. So these are the concepts that are there. Please revise your signals and systems as I have told. So there is nothing much. You can let me quickly get this. Okay, so you may then leave the lecture. Okay, let's